Hi, good morning, and I hope the coffee and espresso is starting to kick in now after the banquet. I'll start with a very pedagogical introduction, and then move on to the meatier matter here, complex phases in the weak interaction, and the phases of VTD, VTS, and the associated CP asymmetries. Then I'll talk about some interesting connections to the charged Higgs, and then in the last 10 minutes cover flavor physics, the next generation, the upgrades that are coming up in the world. So I'm from a Japanese experiment, so I have to start my talk with an apology. I can't cover all the new results from Babar, Bell, LHCB, CMS, Atlas, and the Tevatron, and I borrowed lots of slides from many people. And by the way, this is the picture outside the window of my apartment in Hawaii. But I'm spending most of my time at KK these days. Okay, so the Kibibo, Kobayashi, Maskawa matrix. The important things to note here are first these corners, VUB and VTB. There is where the complex phases live, and there is where the CP violation comes from. And that's what I'll be emphasizing today. The unitarity of this matrix implies that the weak couplings form a triangle in the complex plane with interior angles phi 1, phi 2, and phi 3. And these three angles can be measured in various ways, for example, using psi k short or psi k long decays, or pi plus, pi minus type decays, or rho plus, rho minus, or B to DCPK decays in this corner. At this conference, there were new results on pi 0 from Bell, a number of new results on this angle phi 3 or gamma from LHCB. Especially important was a CPV result in the B sub S mode, B sub S to D sub SK with time dependence. The numerical values of these angles and the lengths of the sides are not important. The critical thing are the answers to the big questions. And those big questions are the determinations of these angles consistent with the determinations of the sides of the triangle? And the other big question, are angle determinations from loop and tree decays consistent? So I know that people outside of the heavy quark field get confused about what we're doing. There's lots of notation. So I want to give a ground roots explanation of what we do. What we do are double slit experiments with particles and antiparticles. And in a double slit experiment, two paths interfere and they have a relative phase. So here we have one path that leads to one final state and another path which leads to the same final state. And in this particular case, over here, the VTD, the complex matrix element, you remember that was in the corner of the CKM matrix. That's one of the two ones with a phase. We measure the phase of VTD, or equivalently, the phase of B anti-B mixing. Okay, so to summarize, this has been done over a decade at the B factories. Here are the results from Bell on one side, from Babar on the other side. We see very clear time-dependent asymmetries, very clear evidence for CP violation, matter-antimatter asymmetries. And we find that the phase of VTD is in good agreement with standard model expectations. Okay, so here's a summary of the situation for these phase measurements. You can see that they all agree very well. The B factory average is very precise. It's a calibration for new physics. We also noticed that in 2013, LHCB has joined this game. I want to point out here a very nice contribution from Spain, which is coming out in a recent review of modern physics this month. So first, Bernard Boll pointed out that by comparing decays with the tagging time greater than the decay time, and vice versa, one could check for T violation at the B factories. This does not assume the CPT theorem. Normally we say we observe CPT, therefore T is violated. This is not the case in this particular exercise. And then the Babar-Valencia group did this experimentally and found a 14 sigma significant signal for T violation. So that's very nice. Okay, so let me just flash one of the new results shown at this conference from Bell. This is a signal for B0 to pi 0, pi 0. Here's the branching fraction. and the signals for B0 and anti-B0 tags. This is a very difficult mode for hadron colliders. Let me continue now with the big picture. So the big picture is this picture, which you've seen at many conferences before, the Wolfenstein parameterization rho and eta on the picture here. You see that everything more or less lines up. So it looks pretty good. I want to point out at this conference, there were a number of new results on gamma, first from the B factories in the past year, but now more and more coming from LHCB with greater and greater precision. Everything looks good here, except for an issue with VUB, which is hard to see, the two circles here. People often misinterpret this picture. They often say, this means the game is over, we're done. But if you try to fit all the data on this picture, this is done by the CKM fitter group, by the UT fitter group, which reported here, Eigen et al. Also reported here. They all find that the following situation. So on this axis is the ratio of new physics to standard model amplitude, and on this axis, a new physics phase. And a 10 to 20% new physics amplitude, that red hot region here, with a large phase is perfectly compatible with all the world's data. Okay, so summary. So far at our current level of experimental precision, the phase of VTD is okay. Now let's look at the phase of VTS. Now B factories can run on the Upsilon 5S, but here LHCB and the Hadron Collider experiments dominate. And you remember, looking at our picture of the matrix, that in a standard model we don't expect a phase here. Okay, so here is the result from LHCB on J psi phi, angular and decay time projections. Now J psi phi is a vector decay. So there are three possible L values, and therefore it's a mixture of two CP eigenstates. This means that the analysis this requires a multidimensional angular analysis, which is quite complex, and I included a slide of this in the backup material. In any case, the conclusion of this is that the new physics phase is small. Now, one improvement on this, introduced by Sheldon Stone et al., is the use of the mode B sub s to J psi F0. Since the F0 is a scalar, this is a pure CP eigenstate. And this provides more statistics, more statistical power per event, and a more straightforward analysis. And it also allows you to display a time-dependent CP asymmetry for the result. And that is shown here. It's consistent with flat. The central value is 1 sigma away from 0. So here is the current situation on the phase of B sub s anti-B sub s mixing, or the phase of BTS. There is one result from CMS, not shown here, and also the results from LHCB are not fully included in this plot. But anyways, you can see this little ellipse here, which is consistent with 0. So far, no new physics phase in VTS. And the standard model does, at higher order, have a very small phase. Okay, so now penguin decays. So here, we have a different process, no longer the box diagram, but VTS contributions. And so we can see if these have an additional phase. Several new results were shown at this conference. And the conclusion is shown here. So look at this narrow band, and then the results of various modes here, starting from phi k short down to F0 k short, omega k short, eta prime k short, and so on. Once again, at the current level of experimental sensitivity, there's no evidence for new physics phases from penguins. It's also interesting to note that LHCB is absent from this game, probably because of the lower k-short efficiency and flavor tagging efficiency. But it does contribute very strongly or dominantly in the B sub s modes. Here, for example, in B sub s to phi phi, they search for a new physics phase. And again, the conclusion is that the new physics phase is consistent with 0. Okay, let me turn to the next physics topic, which are the so-called missing energy decays. Leon Lederman is still up to his old tricks. So one question we might have is, does the brute angular Higgs particle have a brother, the charged Higgs? And so the measurements at B factories and super V factories and hadron colliders take complementary approaches to this important and interesting question. One possible approach, using B to tau nu, an example of a decay with large missing energy, is the following. Normally, this decay is mediated by the W plus. Bu quarks annihilate to a W plus and lepton neutrino. If we know VUB from other measurements and FB from other sources, maybe lattice QCD, then we are sensitive to the contribution of the charged Higgs here. The charged Higgs would modify this branching fraction depending on its mass and its couplings, which I'll explain in a second over here. Okay, a quick consumer's guide to charged Higgs. So Higgs doublets come in several types. Higgs doublets of type 2 couple with different strengths, U and D-type quarks. And the ratio of the couplings tangent beta is the ratio of the U and D couplings. This is the favored new physics scenario in the MSSM, for example. Now, measuring B to tau nu is not so trivial. For example, if we take the semi-electronic decay mode of B to tau nu, it goes to E nu nu bar. So in the end game, we end up with a single charge track plus nothing. How can we do this? Well, at the B factories, or super B factories, these come from the upsilon 4s, so we can remove all, by reconstructing the other side, we can remove all the other decay products from consideration and then deduce the direction of the missing energy and then find these rather mysterious decays. Okay, just to prove it can be done, here's an event display from Bell's analysis of B to tau nu. We can see the decay electron as well as the decay products of the other B, which are removed from consideration. And the clean E plus E minus environment makes this possible. Now, so far with the full B factory statistics, there's only evidence of this decay, no single observation from either Bell or Babar. Examples of the data are shown here. The horizontal axis is extra calorimeter energy after removing the other B, so the signal peaks near zero. Okay, now this already starts to give very powerful constraints on the charged Higgs in these two Higgs doublet models. First of all, shown over here, and then in the blue line shows us another limit from B to S gamma. As we increase the data, this red region sweeps further and further out and constrains more and more of the charged Higgs phase space. Okay, I want to talk about B to D star tau nu, another missing energy decay next. Here again, the decay can be mediated by a charged W or by a Higgs. The observable you measure is the ratio of D star tau nu to D star L nu to reduce form factor uncertainties. And once again, there's sensitivity to the charged Higgs and its coupling. Here's an example from a Babar paper where the kinematic variables of B meson production at threshold are used to isolate the signal, which is shown in green in these various plots of missing mass squared and lepton momenta. Babar also provided a result here at ICHEP 2014 on one of the background modes, for B to tau nu, this little region over here. This is D star pi pi L nu, the first observation of this. Anyways, continuing on with the Babar analysis, they plot the ratio of D star tau nu to D star L nu and compare to what is expected in this new physics scenario. And so here the curve intersects at this point, here the curve intersects at these points. These two intersection points, first of all, are not consistent with the standard model and correspond to different types of new physics, scenarios. So if you go and read the Babar PRL, it says the following: the combination of RD and RD star excludes the type 2 Higgs charge boson with 99.8% confidence level for any value of tangent beta or charged Higgs mass. In other words, Babar found new physics, but they've killed off the 2 Higgs doublet new physics model, which I find very interesting. Okay, so a few points to, first of all, we're still waiting for the Bell update. We hope to hear about that soon. Suppose, if you're a cynical person, that these R values fluctuate back down in the future. What does this mean? Well, this will actually open the door back up to the type 2 charged Higgs new physics. This will allow this kind of new physics to be viable. And it's obvious for beta tau nu and for the beta D star type tau nu decays that we need much more data to fully solve these issues. So that brings me on to the last topic of my talk, which is the new facilities, the next generation. So 2014 is the 50th anniversary of the discovery of CP violation in the kaon sector. There's a conference in London later this week where there'll be a celebration of this. But let's talk about the next generation. Now, the purpose of the next generation was explained on page V of the US P5 report. They said the science driver of these facilities is exploring the unknown, finding new particles, new interactions, and new physical principles. And I couldn't have said it better. Okay. If you want to be more specific, here's a table which lists the observables that will be accessible at Bell 2 and LHCB. I don't expect you to read these all, but you can see that some are in green from Bell 2, some are in red from LHCB. There's a great deal of complementarity, but as I like to remind Director Suzuki of KK, we're also competing and we have to get going fast. Okay. So here's the projection of the luminosity for the new accelerator that will be used by Bell 2, the super Keck B. Bell and Keck B recorded 1,000 inverse femtobarns. Now we've got to change units to inverse attobarns. And the goal is to integrate 50 inverse attobarns and to run at a luminosity close to 10 to the 36th. In Kanazawa's talk at this conference, a slide like this was shown. The key to this incredible luminosity is nanobeams. Very low emittance, very strong vertical focusing. The vertical beam size is 50 nanometers, and that is not a typo. Okay, the work on Super Keck B is proceeding at a good pace. All magnets will be installed by next month. 85% of the 3 kilometers of LER beam pipe is finished. The new positron damping ring has been constructed. Things are going at a breakneck pace. Along with this new accelerator is the Bell 2 detector. It has many interesting features, but I will focus on the new vertexing, new tracking, and new particle ID. So for barrel particle ID, an interesting device called the TOP, or time of propagation counter, is used. Here is a picture of incoming 2GeV pions and kaons, which produce Cherenkov light in this quartz bar, which totally internally reflects down to an array of pixelated PMTs, which are read out with oscilloscope on a chip waveform sampling. That's an interesting collaboration. The vertexing and intertracking is extremely international, starting with the 1 centimeter beam pipe, then depth FET pixels, 2 layers, then double-sided silicon strip detectors, the forward-backward coming from Italy, and then Australia, India, Austria, Japan, plus contributions from Poland, Korea. So this is a very different and very international collaboration compared to Bell, for example. Okay, the software is proceeding at a good pace in Bell 2 as well. Here is a simulation of a missing energy decay. The electron, the lone electron here, and then the B tag on this side. And here is a zoomed view of the interaction region where you can see the depth FET pixel layers and the silicon strip layers. The other facility for the next generation is the LHCB upgrade, shown here. And you can see that the Velo will be replaced. There will be replacements for these tracking systems and scintillating fiber replacements for this tracker. The aerogel will be removed from the rich, new photon detectors and readouts added, and there will also be major modifications of the calorimeter and muon system. Thanks. The feature of LHCB's upgrade that is most interesting and most revolutionary is the upgrade of the trigger. There will be triggerless readout and then a very extraordinary software farm that will do full event reconstruction, run-by-run detector calibration, and then at the end of the day, allow 2 to 10 gigabytes per second of data to be written to storage. This is a very revolutionary change which will allow them to handle much higher luminosities. There's already a brick wall at a megahertz or so in the current system. Here is the schedule for the LHCB upgrade. It starts around 2020. And notice one feature, that the instantaneous luminosity here in the upcoming running period is around 4 times 10 to the 32. It's only a factor of few higher in the next period. This change to the trigger is what will enable a factor of 10 increase in integrated data. Okay, so let me come to the conclusion here. So as I said before, 2014 is the 50th anniversary of the discovery of CP violation in the kaon sector. As I explained at the beginning of the talks, the E plus E minus B factories have confirmed that the Km phase is responsible for most of the observed CP violation. For VTS and other related decays, LHCB has ruled out large CP violating phases from new physics in the B sub S sector. Nevertheless, 10 to 20% new physics effects are consistent with all current data. And these missing energy decays provide important constraints on the charged Higgs. So for the next generation, Bell 2 roll-in will happen in early 2017 with its first physics runs, and the LHCB upgrade will start around 2020. And these facilities will inaugurate a new era of flavor physics and the study of CP violation. Thank you.
We have time for a few questions. Oh, here's one.
Go ahead. I see a few over there.
Tom, I missed the time frame over which Bell 2 will integrate 50 autobarns.
Okay, let me go back to the picture. Yeah, it was going blasting by very quickly, sorry. So if we're starting in 2017, then by the mid 2022, 2024, we hope to be accumulating samples that large.
Thank you.
Could you go to slide 28, please?
28.
That's the exclusion limit about the charged Higgs.
Oh, okay.
This probability that you quote of 99.8%, I believe, is based on the ratio of 2 likelihoods. Is the null hypothesis the best fit for any new physics model, or is the standard model?
No, the standard model is ruled out. That's the zero. That's the zero in this picture.
Okay, what would be the exclusion for the charged Higgs in the type 2 Higgs duplet model with respect to the standard model hypothesis? But how much is the fit worth?
I cannot answer that question. Maybe somebody who knows the Babar analysis better can.
Okay, thank you.
There's one in the corner, back.
When will Bell update B to mu nu? B plus to mu nu?
The paper just went out, or an update with hadronic tags just went out.
Right, but that thing is pretty meaningless because you have a 10 to the minus 3 suppression factor. My estimate is that B to mu nu combined Babar and Bell is at the borderline of observing standard model results. So I don't know why it has not been updated yet.
Okay, thank you for the comment. We should work harder.
I don't see any other question, and if not, let us thank Thomas again.